Can't find my dashboard. Sorry, folks, for the slightly late start here. Hopefully I can figure this out before it's too late. YouTube Studio. They changed things this year and I have not updated yet, but apparently I'm live streaming this, so that's cool. Oops. All right. Okay, so people can see this. I just can't. Okay, it's fine. It'll be fine. Oh, now I can see it. Thanks, YouTube. And I have echo. Sorry. Great start here. Sick. And Anna is now my moderator. So that should be working. All right, cool. Sorry, I had some technical difficulties, but it seems like everything is working now, so that's good. Oh yeah, sorry about the live streamception there. Okay, my sound's still on way too many things. All right, it should be fixed now. So that's awesome. Oh, my headphones came unplugged, so I guess you're just listening to me through the speakers. That would explain why they have issues. And all right, more issues. Cool. All right, it should be fixed now. My headset is now in and plugged in. All right, cool. So yeah, sorry to anybody who is watching this. Hopefully you skipped 3 minutes in. Yeah, sorry folks. I had some issues. It was doing the weird thing again. I had to reboot it. It took like 5 minutes. Yeah, rip. All right. So hey folks. Anybody have any fodder for me to start on? While I'm waiting for people to put in things, I wanted to throw something in from the review I gave out today. So the people who did not have me today probably have not seen this before. Well, they definitely haven't seen this before unless they looked at the answers online. Early AP review, no. Where's my review for the test? Oh, super organized here. Well, never mind. I totally thought I had that on here. Where would people like me to go first, since nobody has given me anything as of yet? Do 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 do. 17, 54 on the review. All right, 17. Let's see if I can find that one. And 8. So what do I got? I got this one. I got this 54 on this one. No. All right. So that's not the right one. That's not the right one. Whoa, that's like, okay, that explains why I don't have what I want. That's not the 154's on. Man, I am really kicking butt right now. 17, 17. All right, lesson 17. Oh, okay. 54 on the review. That is the AP. I'm really confused, folks. I'm gonna switch to some more Inception stuff because I need to go grab more stuff off of my flash drive, which I guess I'll stream. So, yeah. Sorry about the lack of professionalism here. This has been my worst one yet. I spent a while looking for this thing. So yeah, it's not in what I prepared. Feels bad. Optimization 1 and 2, optimization review worksheets. Oh, it was already on my desktop. Okay, okay. Optimization 1 and 2 combined. Okay. So, oops. Lord. Need to plug in my keyboard. I very much apologize for the start. I'm going to have to edit this video when I upload it so that it does not include those first parts. All right. Whoops, I don't want optimization now. Oh, I do want optimization. Never mind. Why is it? Okay. Mr. Kennedy is very confused right now. Just chuck some random stuff on here. And then look for the chapter 3 review here. Chapter 3 multiple choice questions. That would be a fantastic place to go to not be a complete and utter deadbeat. All right. Where do I have this other thing on my desktop already? All right, whatever. Okay. I don't know. Thank you for turning my sound back on, computer. Some people are asking me about reading derivative and second derivative graphs. I definitely want to do that. That's part of 17, so that's something Philip's talking about. Sam's laughing at me. 54 on the review. I am gonna find that darn review. This is why you prepare ahead of time, kids, and I normally do, but technical difficulties wrecked me. There's no 54 in that. Blast. Hey, I got it. 54. All right, feels good, man. Finally. A solid 11 minutes of lack of professionalism, and we're going to go straight on with professionalism from this point on. All right, so 54 is where I wanted to start, and then I'm going to jump into talking about lesson 17, where I'm going to go a little more free form, because I can just draw pictures and answer questions about them pretty easily. But here we got an offshore oil well that is 2 kilometers off the coast. So when you're drawing this picture, you should have a coast and an oil well. And the refinery is here 4 kilometers down the coast. So what we have here is, this side's 4, this side's 2, and we have some sort of like triangle here. And what they tell us is that laying pipe in the ocean is about twice as expensive as it is on land. And I'm gonna, oh yeah, I'll go back to using my other headphones in a sec. Okay, so I don't want to go straight across from the refinery to the oil well because it'll cost twice as much for the whole distance. So to make it more efficient, I need to go somewhere in between here. It doesn't make sense to go straight across because then I'm paying double price for going along 2 and then single price for going along the 4. I want to like cut the corner somehow, but because it's twice as expensive, I don't want to cut the corner too much. And so what I need to make is, I need to split this distance in terms of 4. So I'm going to call the little short distance x, and I'm going to call the rest of the distance to the refinery that I go down the coast 4 minus x. So really, my picture looks something like I have a refinery, or my refinery's here, my oil well's out here. Here's my oil well. and I'm going to go somewhere at an angle, and then I'm going to cut down the shore. So that's where my picture is. Building the equation now is pretty easy. My money is just going to be, since it costs double to go through the ocean, it's going to be 2 times this distance, which I'm going to call, like, I don't know, C. And it's going to be 1 for the other distance, the length of the shore, which is 4 minus x. And here I have 3 variables, which is garbage, but luckily I can figure out C here in terms of x. Because I know this side is x, I know this side is 2, so C here is the square root of 4 minus x squared. It's what you get when you do 2 squared plus x squared equals c squared, and you solve for c. So you just square root both sides. Whoops, 4 plus x squared. As I check my work. And then I just chuck that back in my equation, and I get that the money equals 2 times the square root of 4 plus x squared. Plus 4 minus x for the cheaper part, the part where it's half as expensive to go down the shore. And then I just take a derivative, and I get 0 equals 2 times 1/2 this 4 plus x squared garbage to the negative 1/2 times the chain rule part, which is 2x. And my derivative of negative x is just negative 1. And I just solve this equation now. The 2 and the 1/2 just straight up cancel each other out there. I add my 1 to the other side, and I'm going to go up to the top of the page here. And I get 1 equals 2x. And instead of times 4 plus x squared to the negative 1/2, I'm going to say it's over the square root of 4 plus x squared. And this makes it easier to solve. Now I just multiply the root 4 plus x squared on both sides, so to the other side there. And I get root 4 plus x squared equals 2x. I just do some squaring of both sides. I get 4 plus x squared equals 4x squared. I subtract x squared and get 3x squared equals 4, and you may see I'm home free. X equals the square root of 4/3. Or the negative square root of 4/3, but you know, they mean the same thing in this case. You're going for root 4/3 down the shore in any case. And that's it. I'm going to say this is root 4/3 kilometers. And I'm happy days on that question. All right. Let's see. James Fay wants some rice. Well, I can't help you with that, James. All right, that's that guy. I'm going to put my headphones back in. So let's close my folder. And ensure that this is still working. It is. Out of curiosity, am I quieter or louder with these headphones in? Because it looks like I might be louder. All right, so let's talk about quiz 17, because that question came up. And there's like kind of 2 pretty important facets of that one. So let's kill all the stuff from the last live stream and get rolling here. Oh, I'm louder now. Oh, seems good. Okay, so quiz 17. It really has 2 parts that are relatively different. I have the mean value theorem, and I have reading derivative graphs. And those of you who got the review already know that these are extremely important. Like, both of these are heavily showcased on the review. And yeah, for good reason, they're pretty important sections. And those of you taking the test on Friday are going to have the quiz on your test, which has this quiz 17 on it. Okay, so the mean value theorem. All it says is if I make any graph here, let's make something that looks like this. If I take any 2 points on this differentiable function, by differentiable I mean it's continuous and its derivative is continuous. If I pick any 2 points on this thing, so the endpoints, or let's pick this point, so I'll call this A and B and C. What it says is that the average rate of change between those 2 points must equal the actual slope of the graph at least 1 point. And in this case, on my BC, it's pretty clear it happens somewhere around here. And a lot of mean value theorems make you find the x value where the average slope equals the instantaneous slope. Some other ones make you find b so that you can prove a certain slope exists on this interval. If you don't understand what I mean by that, let's say c is at 7, 1. And let's say I'm trying to look for a place where my average, or I'm looking for an interval where the mean value theorem says I must have a slope of -1. Well, if I must have a slope of -1 somewhere on the interval, based on the mean value theorem, I need to pick a point such that my average rate of change is -1. So let's see, what's my best chance on this graph? Like maybe here at this point. And let's say that is something that actually makes this work. What would that be? Like, let's call it 3, 5. That seems like a believable x and y coordinate on that. If you look at my average rate of change, I'm going down 4 over 4. That's a slope of -1. And so somewhere on that interval, I have to have a -1 slope. So this is a way of using like pre-calculus math to prove that a slope has to have occurred somewhere on that interval. And that's like a kind of a big idea of the mean value theorem. In the case where you actually have to solve for the x value, all you need to do is take this average slope guy and set it equal to the derivative of the function. So you'll have to know the function to do that. Or in the case of the free response problem I gave the kiddos today, you can just read points on a graph and figure it out from that. But yeah. All right, the other half is derivative graphs. So I need another beautiful graph. This graph is going to be of the derivative. So this is a y prime graph. And I'm going to make it do some interesting things just so we have some stuff to talk about. That looks like a fun graph. So a few things I have in this derivative graph is I can talk about increasing and decreasing. I can talk about where I have maximums or minimums, not absolute maximums, but both local or relative maximums. There are situations where I can find absolute maximums and minimums by reading these, but they're a little more nuanced. And I'll talk about that in a little bit. So yeah, okay, let's talk about absolute maximum too. In these sort of graphs. But I don't just have that. I can infer stuff about the second derivative also, which is the concave up, concave down, and I can infer about my inflection points. So I'm going to do all of these things. So points where I'm increasing. Since it's a derivative graph, where the derivative is positive, is where I'm increasing. So I would be increasing like on this part, on these parts right here, anywhere I'm positive, and over here. And that's increasing. All right. Next. And oh my gosh, the erase tool is so useful for this. Okay, so next, decreasing, it's where I'm negative, so that's down here and down here. So on those intervals. All right, next. Where do I have a maximum? I have a maximum where my graph switches from a positive slope to a negative slope, increasing to decreasing. That's a maximum. And so here I switch from positive slope to negative slope. And by that I mean positive values in the slope to negative values in the slope, since this is a slope graph. And I also have that happening here. And so there's 2 points I have local maximums. My 2 points where I have local minimums are, oh no, I destroyed my axes. Are the other 2 points I go through the axis, where I switch from negative slope to positive slope. And that's here and here at those points. As far as absolute maximum go, let's say I set up an interval where I'm going from here, from my starting point at 0 here all the way to this point. So I'm really only looking at this interval here between 0 and whatever this point is. I'll call it 3 for giggles. I can figure out where the absolute maximum happens on this, because no matter what my starting value is here, which I have no information about what it is, but it's just something, I could call it 0. I'm going up here because this is all positive slope. And then after this, I switch to a negative slope until I hit the end of my interval, because they're all negative values. So this point here, which was a relative maximum, would be the absolute maximum on the interval, no matter what my starting value is. And so we can actually figure out stuff about absolute maxes and mins from our derivative graph. Yeah. Let's move on to concave up and concave down. Concave up is where my derivative graph is increasing. So that's where the slope of this graph is positive. So that would be between these 2 lines, this section. And on this section, between that critical point and that critical point of the derivative graph. And then from, I guess, 3, as I labeled it here, on, those are all positive slope sections of my derivative graph, which is concave up. For concave down, it'd just be all the other ones, all of the negative slope sections, which are from negative infinity to whatever this critical point is. So this section, here where it's decreasing, here where it's decreasing, and that's it. And lastly, all of my inflection points. Inflection points are some of the most family friendly, because most people, when they see this, really want to do something with the critical points of this graph. And the critical points of this graph are 4 inflection points. So if I'm looking at the derivative graph, where it has maxes and mins, those are all inflection points. So this graph actually has 5 inflection points. And hopefully this was helpful, because there is a crud ton of stuff you can get from derivative graphs. And you should not be rattled by these, and you should apply the knowledge from these to reading derivative equations and reading other sort of problems, because this helps you shortcut so many of the problems, especially in our review, are way faster if you have a really strong understanding of your different layers of the derivative. All right. Where do we go next? Looking through lesson 17. 19 minutes late. Can we do 29 on the optimization worksheet? Can you do 6 from the second review? All right, so let's do 29. So I got to open the right worksheet here. Which one is that? That is probably this one. Yeah. All right. So I did not do this one in every class. I know I did it in 8th today. But let's roll this guy. Oh, yeah, I just didn't put the picture in it. That was a rookie mistake. So let's make sure the picture's in my sketch here. Can I zoom in on this? Oh, yeah. Sick. All right. So, okay. A lot of people get rattled by this whole inscribed thing. It's really not that intimidating. This x and y are my x-coordinate and my y-coordinate. It turns out they tell me what my y is. It's root 25 minus x squared. My x-coordinate is just x. So that means this is x. Unfortunately, my rectangle is not x long because it goes x in the positive direction and x in the negative direction. So there's another x here. And so this rectangle area equation is just simply 2x long and root 25 minus x squared tall. Okay, then we can slam a derivative right away. We get 0 equals 2 times root 25 minus x squared. That's a prime b, where this is a and this is b. And then 2x times, and I, of course, did not leave myself enough room here. Well, best effort. Times 1/2 25 minus x squared to the negative 1/2 times negative 2x. For the chain rule here. So this is a b prime. I'm going to do some simplification, clean up, and get this back in the middle of the screen here. So I get 0 equals the 2 root 25 minus x squared doesn't simplify at all. But this next piece does. 2x times 1/2 is x, times negative 2x is negative 2x squared. And same as I did on 54, I believe, I'm going to take this square root garbage and chuck it on the bottom as a square root. 25 minus x squared. Then I just add the 2x squared over garbage to the other side. 2x squared over root 25 minus x squared equals 2 root 25 minus x squared. I multiply both sides by root 25 minus x squared, and all of a sudden things open up for me. I just get 2x squared equals 2 times 25 minus x squared. The square roots all go away. So I get 2x squared equals 50 minus 2x squared. I add 2x squared to the other side. I get 4x squared equals 50. I divide by 4. I get x squared equals 12.5. And I get to the end here where x is the square root of 12.5. Now it asks, what are the length and width of my rectangle? That's not x by y. So I actually did not finish the problem adequately in the classes where I've gone over this, which is kind of funny. Because x is root 12.5, but this side of the rectangle is 2x long. So it's 2 root 12.5 long. And then I got to figure out what y is. But if you chuck x back in here, you just get 25 minus 12.5. So y is also root 12.5. And so this is 2 root 12.5 by root 12.5. And that's it. There are no units, so we're chilling. Let's see. Is my mic maxing out and popping itself? Gosh, I hope not. I can turn it down a little bit if that's actually an issue. I can turn down my mic a little. Okay, yeah, it should be lower now. Let's see the next question. Can you do number 3 on optimization part 2? Yeah, that seems good. I'm happy to do that. Yes, thank you for making fun of the fact that my hand hurts. I appreciate that, kids. Where are we at? I think it's this one? No, that's the wrong one. That's the wrong one. Here we go, number 3. A company manufactures cylindrical barrels to store nuclear waste. I believe that is it. Oh, I turned it down too quiet. Okay, Nikhil's just done. All right, so, yeah, okay. So I turned it up a little bit more. It's better now. Ugh, gosh, your speakers probably just suck, dude. All right, so I pop into Screen Sketch here. And I didn't do this one in any classes so far, so this should be new. So this is the cylindrical barrel one. Cylinders look like something like that. It costs a different amount. It costs 10 for the top and bottom here. And yes, I know my picture sucks. And it costs 8 for the sides. We have two equations here. We have a volume equation because they tell us the volume. So pi r squared h, which is the volume of a cylinder, just equals 5. And then our second equation is the money equation. We actually don't use the surface area equation because we care more about the money. So it's going to be 10 times the surface area of the top and bottom, each of which are pi r squared, and I have 2 of them, so times 2 pi r squared. And it costs 8 for the sides. The sides, that wrapper thing, if you unwrap it, it is 2 pi r long, the circumference of the circle, and the height tall. So that's going to be 2 pi r h. And as you notice, we have 3 variables, h, r, and money, so that sucks, but that's why we have this other equation. And so I just solved this other equation for one of my variables. I'm going to choose h because r has multiple of them and h is easier. So h equals 5 over pi r squared. I plug that back into my other function. I get money equals, I'm just going to simplify this as 20 pi r squared. And I'm going to simplify this as 16 pi r times 5 over pi r squared. There's a significant amount of simplifying that happens now. This r kills one of these r's. This pi kills this pi. And so I really get my money equation equals 20 pi r squared plus 80 over r. And we're in nice land for optimization problems. We can just take the derivative, set it equal to 0. We get 40 pi r minus 80 over r squared. Just add the 80 over r squared to the other side. I multiply both sides by r squared to get rid of a denominator. I divide by 40 pi on both sides, so I just get 2 over pi equals r cubed. And so r is just the cubed root of 2 over pi. And I just need to find my h. So h equals 5 over pi times the 2 over pi dude to the 2/3. And I'm good to go. Those be my dimensions. I guess I should put units on them so they're in feet. So that's what the problem's in. And I'm happy. Yeah, Apple earbuds are garbage. I agree, Nikhil. I hate most Apple products because they don't let me program them to be the way I want. Let's see. What are the equations we need to know? Okay, like the revenue equation. So, hard area and volume equations, I'll definitely give you. Revenue equations, you just got to figure those out. Like for example, on the one just below, 4, you need to know that the maximum revenue is the number, like the weight of the cows. So, weight of cows times the number of cows. So this isn't a revenue equation, but it's like a total weight. It's like optimal weight or something I'm trying to maximize. And so building an equation like this is something you can build or figure out from the context clues of the problem. And so that's not something you memorize so much as you like practice building those sort of equations. So you do need to know how to build revenue equations. There's no like accounting equations that you need to memorize or anything. That's for a different class. So yeah, no worries there. Let's see. Nathan had an actual question somewhere a while back here. that I ignored. Can you do 41 on that sheet? That would be a place, yeah. Yeah, let's go look for that one with 41 on it. This one. Yeah, okay, this one's like extremely algebra heavy, so we'll see if I can get it to fit in one section. So a lot of people got rattled by the basically the equilateral triangle is pretty rattly. You have two shapes. You have an equilateral triangle and a square. The square is really easy. If you call one of the sides x, you call the other side x. Its area is x squared. Wow. Area of an equilateral triangle, if you have the internet, is pretty easy to look up. But it's a little more complicated in terms of like the sides. I called all the sides b. I don't know why. You can call them whatever you want. But the area equation is not like 1/2 b squared or something nice like that. We have to split this triangle in half, which builds 30, 60, 90 right triangles. And then use the properties of the 30, 60, 90 right triangle to figure out that third side, or use trig. They're the same thing. So if I cut this side in half, the way I cut this triangle in half, this side's b over 2, and so this side is just root 3 times b over 2, or root 3b over 2. And that's the actual height of my equilateral triangle. So this is just some like SAT crap here. And that's what I need to build my area equation. So my perimeter is easy. There's 3 b's in this problem, one around each of the edges because there's 3 sides. And there are 4 x's. And my perimeter is 10, so I'm just going to erase that and chuck a 10 in there. And that's my perimeter equation. And my area equation is going to leverage all this stuff I figured out over here. X squared for the square. And my base, so plus 1/2, because 1/2 base times height. My base is just b. And my height is root 3 over 2b. And those are my 2 equations. Oh, we're back. Not like this. It crashed. We missed all that. Huh. I can still see it right now. Oh, I guess it's really laggy. It's super behind. Weird. Huh. It advertised? It should not be doing that. Let me check my, yours is still dead. Mine is, I'm watching it right now and it is updated. Like I'm looking at, it's behind, but it's still there. Let's see if I can zoom up to regular time. All right, I think we're back. Okay. So all I did was build these perimeter and area equations. This one's my perimeter equation, very easy. A triangle has 3 sides. A square has 4 sides, so 3b plus 4x. And my area equation based on the area stuff I figured out over here, 1/2 base times height for 1/2 base times height, and just side squared for square. Then I just solve for a variable in my perimeter equation and plug it back in. It's less intuitive here which one is better because they're both things squared in the area equation. So I'm just going to pick one randomly and solve for x. So I get 10 minus 3b equals 4x. So I get x equals 2.5 minus 3/4 b. So I just did the division by 4 now. A lot of people get ultra rattled trying to square things with denominators, so just avoid it by simplifying things ahead of time. Okay, so I solve for x, so I'm plugging that in for x in my area equation. I get 2.5 minus 3/4 b squared. And over here I get root 3 over 4 b squared. I have a little more, simplifying to do before I take the derivative, because I should simplify this inside. I get 6.25 minus, what do I get for my inside ones? They're both negative 7.5 over 4, so negative 15.4 when I add those together. B. Plus 9/16 B. When I square 3/4, I get, or B squared. When I square 3/4, I get 9/16. 3 squared over 4 squared. And that's plus root 3 over 4b squared. Now I just slam a derivative on this. The 6.25 goes away. I just get a negative 15/4 plus 18/16 b for just multiplying the 2 by the 9 and dropping the power by 1 plus, I guess if I'll just write it 2 root 3 over 4b for this guy. One thing I like to do here at this step is multiply by something so all my denominators go away. And that thing I can multiply by is, I guess, 16. So I'll do that. And I'll get negative 60 plus 18b plus 8 root 3b. And all I did was multiply everything by 16 there. So for multiplying something like a fraction, remember it's 16 divided by 4 is 4 times 2 is 8. That's why I got 8 root 3b. You add 60 to the other side, you get 60 equals 18 b plus 8 root 3b. And you factor out the b and divide by the crap to get what b is. So you get 60 over 18 plus 8 root 3. And I definitely could have picked something better to multiply both sides by to get rid of all the denominators, because this can be simplified now. And I get 30 over 9 plus 4 root 3. And that's in no units. Sick. Then I just need to find x, so I plug this crap back into the other equation. I get 2.5 minus 3/4 times b, which is 30 over 9 plus 4 root 3. And that equals x. And we're done. That's that problem. And yes, those are some janky parts, but it's okay. Let's see. Dang, how has Tribble not gotten banned yet? Let's see, where do I have another question now? Ben Shabiro. Alright, that was a comment. We'll notice in 15 minutes. Naira, I don't super want to go over 25 because we did that problem in class almost exactly with just slightly different numbers. And so it's algebraically tedious and exceedingly similar to the bottom question in our notes. I would prefer not to do that guy for repetitiveness issues, since you can generally look at that. Yeah, sorry to shoot that down. Anybody have any general questions? Since I did a lot of optimization, please remember that optimization is about 10% of this test. Or if you're taking it Monday, about a little more, 15% or something. And so the really important stuff is knowing all the derivative crap and maxes and mins and absolute max and mins and induction points and all that stuff I talked about earlier. Arithmetic with large numbers. Yes, I know, Drew, that you can't multiply things. Um, let's see if I could do some things that yeah, I'm not answering that question, Nick. All right, so if you want to multiply large numbers, remember there are cool tricks like this. If you need to multiply 36 by 41, remember that you can multiply 36 by 40. And that's doable, because you know what 36 times 4 is. It's the same thing as 18 times 8, or 9 times 16, or so on and so forth. Any one of those that gets you there. But really, 36 times 2 is 72. 72 times 2 is 144, and you add a 0. And then all you do is you add 36 to that, because we have one more 36 if we're multiplying by 41, and you get 1476. And that's a great way to multiply two-digit numbers. How does the test outline look? Related rates. Dude, Philip, your chances of getting a related rates problem are pretty decent, but there's probably only going to be one. So covering all of related rates again, check my last live stream. Let's see. How does the test look like? Okay. So I don't remember exactly, but it looks something like 13 multiple choice questions for those of you on Friday. There's a quiz next. Actually, I don't know the exact order, but there's a quiz on the no calculator part, and then there is the free response question. The free response question looks exactly like, I have an example, so I don't need to just wing it. It's somewhere here. Where's the... Oh, it's on the back of this, isn't it? Yeah, it looks exactly like these things. This one is the one from last year, so that one's garbage. Where's my 2018-19 one? There it is. So it has critical points, relative max, relative min, inflection points, all this crap. One of these questions is on the test. And then going back to my screen sketch. So that's the free response. And the free response is designed to take you about 10 minutes. To do everything in one of those questions, I think 10 minutes is pretty reasonable. The quiz is designed to take you about 15 minutes, maybe 20 minutes. And the 13 multiple choice are about 25 minutes. And as some of you know who've started slamming on the review multiple choice ones, some of them are really, really fast, and some of them take a little while. So time management skills are pretty important for doing that. So we're looking at like a 50 to 55 minute first part of the test. And then the second part's just 5 multiple choice questions with a calculator. So this is all no calc stuff. So this test is like, this is going to be like 14 minutes. It's like a really long no calculator section and a really baby calculator section. And that's kind of what to expect here. Is my hand feeling better? Yeah, a little bit. And yes, Drew, you can do the same thing for 3-digit numbers. That's how I do them in my head. Yeah. I'm not like those awesome dudes who do TED Talks who can like multiply 3-digit numbers in seconds. I actually have to do math. Can I do another live stream? No. No, that would be incredibly stressful. I'm good. And I need to go to the doctor for my hands. I got things to do. Oh, one thing I really wanted to talk about. Definitely. Did I end up putting this on my desktop with all that? Chapter 3 multiple choice questions. Kennedy. That's it. Cool. So I wanted to zoom down to this question right here, because this question is one a lot of people will think they do right, and then they'll check the answer key and be like, I did this wrong. This question says, when is the speed of the particle increasing? Based on the fact that we know its position is a vector quantity, speed is a scalar quantity. So we get some sort of disconnect here. This makes this question harder. This is like that first warm-up question where a bunch of people were getting tilted about the whole decreasing and increasing rate and like what that actually means. This is where that comes into fruition. So in this question, clearly, since we're talking about speed, we need to find velocity, which is the derivative. So I take a derivative. I need to find the critical points of this guy, so I need to try to factor this guy. It's going to be 3t and t. I'm probably going to use, 4 and 2? So yeah, it works like that. Sick. I get a negative 2t here and a negative 12t here, so negative 14t. My two critical points are t equals 2/3 here, and t equals 4. And so far, we seem good. Then I take, and this is the part where, okay, so I should test on either side of these first. I'm going to test 1, 5, and 0. At 0, my derivative is positive. At 1, my derivative is, well, let's plug it back in. I get 1 here and negative 3 here. That's definitely negative. And at 5, my derivative is positive. So I know my increasing and decreasing interval there. But that's where the velocity is increasing. That's not my speed. I need more information. And so I go to my second derivative. And I go to 6t minus 14 is my second derivative. That's my acceleration equation. And a lot of people want to say, hey, when your acceleration's positive, your speed's increasing. But that's not true. If you have a negative velocity and your acceleration's increasing, it means your velocity is getting less negative. And that's a decrease in speed. So we need to actually also find the intervals of the second derivative to see where these match up. And so that's pretty easy. T is going to be 14/6, or 7/3, what makes this 0. And so that's this guy's critical point. And I can test values on either side again, like 1 and 5. The same ones I picked over here. And if I plug 1 in this equation, I get a negative 8, just up here in the second derivative. And if I plug 5 in, I get a positive. And so I'm decreasing before 7/3 and increasing after. And what I need to do for my answer is I need to figure out where either both my derivative and my second derivative are decreasing, or where my second derivative and first derivative are increasing, because either a negative slope getting more negative or a positive slope getting more positive are both speeding up. And so if I look, my second derivative is positive after 7/3, and my first derivative is positive after 4, so they're both positive after 4, because 4 is bigger than 7/3. So I know instantly it's not these two guys. It's got to have that 4 to 10 interval in it. But it also can be where both the second derivative and the first derivative are negative, because that's like having a negative speed and getting more and more and more negative. So my slope is negative from negative 2/3 to 4 in between these two guys, and my second derivative is negative before 7/3. And it turns out 2/3 comes before 7/3. So from 2/3 to 7/3, I'm negative negative, and from 4 to 10, I'm positive positive, and both of those are speed increasing. So if you get a speed problem, know that there is a lot more work that needs to go into that. I had to do a ton of analysis to get to that point. So yeah, just be aware of the whole speed conundrum. And it lets me review a whole bunch of first and second derivative crap, so I'm pretty happy to do all that too. Let's see. Where else did I have questions? Interpreting derivative and second derivative graphs. If you missed the first half of the stream, somewhere like 20 minutes in, I did a huge talk about how to read derivative graphs. So that is definitely in here. How can velocity be negative? Yeah, going backwards. Good answer, Spectre. Let's see. Any other questions? Or yeah, we got 3 more minutes. I can do one more. Can you do problem about solving concavity? Sure. I kind of did it here because I did second derivative, but I'll just do one from scratch here. So if I just take any function, let's make a random thing. Let's make it 2x to the 6th minus x to the 4th. This is a beautiful abomination of a thing. So I take 2 derivatives because that's where I find concavity. My first derivative is 12x to the 5th minus 4x cubed. My second derivative is 60x to the 4th minus 12x squared. I need to solve for the zeros of this, so pretty clearly I can pull out a 12x squared. And all I get is 5x squared minus 1 in my remaining parenthesis. So my pips, my possible inflection points, or places where the concavity changes, are x equals 0. That's the easy one. X equals the square root of 1/5. And you get that by solving for where 5x squared equals 1. You divide the 5 and square root. And x equals negative root of 5th. So I put those in order so I can pick values in between them. The square root of a 5th is, I don't know, but half times a half is a 4th, so it's something a little less than a half. So picking values between that and 0, I'm just going to pick 0.1 and negative 0.1. That's one of my go-tos because it works a lot when you're doing values around 0. On the edges, I'm just going to pick 1 and negative 1, since I know this is somewhere a little less than a half or negative a half for the root 1/5 and negative root 1/5. Oh gosh. Okay, my stream did not crash. All right, cool. And then I just plug these into the second derivative. Now, some tricks. Both of these are squareds. So the negative and positive are always going to match for the mirror values because x squareds are always positive. 0.1 squared is 0.01, which times 5 is still way less than 1. And so both of these guys are decreasing on that interval because the negative 1 wins and is multiplied by a positive 12x squared. But if I plug in 1 or negative 1, I get 5 minus 1 in this last parenthesis, which is positive for both of those. So I have an inflection point at x equals negative root 1/5 and x equals root 1/5, not at x equals 0. And I'm concave down from negative root 1/5 to 0, and from 0 to root 1/5, bleh, which is between my middle 2 sections, where I'm concave down. And I'm concave up on either of my edges, so I'm concave up from negative infinity to negative root 1/5, and from root 1/5 to infinity. And that's it. That's one of these problems. You always do them the same. You look at the pips, you test in between them. Anywhere it changes, you got an inflection point, and then you just give your up and down in there, and we're good to go. All right. I think we're good. I think we have answered most of the questions. I really have to go to the bathroom, and it is 8:01. So thank you, Anna, for shutting off some of the bad conversation from previous year students. I am not going to go play video games. I'm going to go work out my hand or something. So have a great night, y'all. Sorry about the technical difficulties at the beginning. Technically, this is only like a 15-minute stream. But I'm pretty tired, so I'm going to go check out. So thank you all for coming, and see you soon.